A spy tracks a rocket through a telescope in hopes of determining its velocity. He is 10 kilometers away from the launch site, and his instrument shows that the angle between the ground and the telescope is changing at a rate of pi/12 radians per minute when the angle is pi/6 radians. How fast is the rocket going at that time? Okay, so at this point you're probably like, what is this question even asking? So when we're doing word problems, I really recommend you read it through multiple times, and I like to try to underline main things. So a spy tracks a rocket through a telescope in hopes of determining its velocity. So we've got this rocket, terrible picture, but you know what I mean. And we've got this spy who's on the ground. I'm just going to put him on the ground with a telescope. I told you guys I'm not the greatest of drawers. Okay, so he's 10 kilometers away from the launch site. So the rocket obviously is going to start at a launch. So we know he's 10 kilometers away from this launch site. The instrument shows that the angle between the ground and the telescope, so there's the ground and the telescope, so we'll call that theta, is changing at a rate of pi/12 radians per minute. Okay, so we know that the rate of the theta is changing at pi/12 radians per minute. When the angle is, so we need to figure out, okay, and that's when the angle is pi/6 radians. We want to know how fast, so that's the velocity. So how fast is that rocket going? Okay, so let's say this is, we've got our h value. So how fast the rocket's going would be the derivative of h over time. So how quickly that height is changing. So that's going to be the velocity of the rocket. It's how fast that height is changing. Okay, and that's going to be in terms of, let's see, what did they tell us? Kilometers. So kilometers per minute. Okay, and we're letting h be the height or the distance from the rocket to the ground. Okay. All right, so we know these are the things that we have. These are the things that we know. We also need to define theta. So theta is the angle between the telescope and the ground. Oops. Okay, and this is in terms of radians. And this is in terms of kilometers. Okay, so I've got my variables. I've got my rates. I know I'm trying to solve for dH dt. That's what I'm trying to solve for. So do you see how a problem that seemed really sketchy, by reading it a second time and kind of drawing a picture and assigning variables as we read it through a second time, makes it a lot easier to go through? Okay, so I need to find a relationship between theta and height, and I think we can do that using right triangle trig. This is the opposite, this is the adjacent. So that relationship is going to be the tangent of that angle equals the opposite over the adjacent. So now I have found that. I'm going to actually solve this for h. So h equals 10 times the tangent of theta. That way we don't have to deal with fractions. Okay, so I have now done step 4 where I found a formula that relates those two variables together. So now, again, I'm solving for a rate, so let's take the derivative of both sides. So I'm going to get derivative of h with respect to time equals the derivative with respect to time of 10 tangent of theta. So dH dt equals 10. And then again, I'm doing this with respect to time, and that's a theta. So that's going to be the outside function, which is the derivative of tangent is secant squared, evaluated at the inside, times the derivative of the inside. So now I've got this formula. I know I'm solving for dHdt, so I need to see if I have values for theta that I can plug in and for the rate of change that's happening to d theta over dt. So we know that d theta over dt is pi over 12, and we know it's positive because as this rocket is going up, this radius is going to be getting bigger. So we know that. Okay, now they also told us we're trying to find it when our angle is pi over 6. So we have values now we can plug in for here and we can plug in for here. So that's going to give me dH over dt equals 10 secant squared of pi over 6 times, I found that the derivative of theta with respect to time was pi over 12. All right, so that's going to give me, so secant squared is the same thing as 1 over the cosine squared of pi over 6, all still times pi over 12. So that gives me dH over dt equals 10 times 1 over 3/4 times pi over 12. This is really ugly, but we're going to go over here now. So I've got dH dt equals 10 times 4/3 times pi over 12, which gives me, let's simplify these out if we can. 4 goes into 12 3 times. So that's going to give me 10 pi over 9 kilometers per minute. Okay, so in case you got lost where this 3/4 came from, the cosine of pi over 6 is the square root of 3 over 2, and when you square that, the square root of 3 over 2 quantity squared, you're going to get 3 over 4. Okay, so I have that rate of change. So again, we always want to write these in terms of sentences to kind of end this whole thing up. So the rocket is going 10 pi over 9 kilometers per minute when the SPICE telescope is at an angle of 10 pi over 9 kilometers per minute. Water pours into a large rectangular tank with base 2 feet by 3 feet at a constant rate of 5 feet cubed per minute. Determine the rate at which the water level rises. Okay, let's draw an image of this. So if I've got a rectangular water tank, again, don't judge my drawing. Okay, it kind of looks like that. Hopefully you can visualize we've got water. The water's pouring in, so obviously that water is going to be getting more. Okay, so I've got a picture of it. So it's a rectangular tank with a base of 2 feet by 3 feet. So let's label those pieces. So I've got 2 feet, 3 feet. Okay, and we know that I'm looking for the water level. So let's call H this water level. Okay, so let's let H be the water level. So that's going to be in terms of feet. Okay, we know that the rate that the water is pouring in is a 5 feet cubed per minute. So if we're looking at, when we hear that, that should hopefully tell you volume. It's how much it's changing. Again, it's how much water is going in. That's the volume of water that's getting put in. So let's let V equal the volume of water in terms of feet cubed. So then if I was looking for, I'm solving for dH dt, and that's going to be feet per minute. And I know dV dt is 5 feet cubed per minute. Okay, so again, I'm solving for that. I know I'm trying to figure out how fast is this water's height increasing over time. Okay, so I'm solving for that dH dt at specifically when that volume is going. Okay, so if I'm trying to find that, let's see if we can find some type of relationship. So if I'm relating these quantities, we know the formula for the volume of a cube is length times width times height. So I know I've got 2 times 3 times h. So I've got a formula, V equals 6h. So we've got the hardest part down, which is finding that formula that relates the two quantities. So now we'll go through and we'll do that implicit differentiation to get this in terms of rates. So the derivative with respect to time of the volume equals the derivative of respect to time of 6h. So dV over dt equals 6 times the derivative of h with respect to time, because again, we're finding the derivative with respect to time. These are functions of time. Those are going to change as the time changes. More water is coming in. Okay, so now let's plug in what I know and what I'm solving for. So I know that the volume is increasing at 5 feet per minute, feet cubed per minute. I don't know that dH dt, so solving for dH dt, I get 5 over 6. And that's going to be feet per minute. So we would say the water level rises at a constant, sorry about that dog, he's really cute if you could see him, rate of 5/6 feet per minute.